So welcome everybody to this webinar. It's the Wales and West branch who've been able to get Robert Luckwell to come and he's happily volunteered to speak to us about water treatment process. It's really aimed as an introduction to water treatment, and Rob's been working at Bristol Water now for 18 years as a water quality scientist. He's still hugely passionate about the subject, and he gets heavily involved with all sorts of internal and external sessions, presentations, and just sharing his knowledge on water treatment. Bristol Water has quite an active foundation, which is like an academy for younger schools. He also presents to universities, and it's been really good that he's been able to come and join us today. For those who haven't come across Pipeline Industries Guild, it's an organisation that spans across all of the pipeline industries: oil, gas, water and wastewater. And that's one of the aspects that I find really good about it, a chance to pick up on what other industries are doing and broaden your horizons. There's a very vibrant professional development network for those starting out in the industry, and it's a brilliant way to network. There's as Rob mentioned earlier, there's a massive back catalogue of these webinar events. If you want to go back through, just Google Pipeline Industries Guild YouTube channel, and you'll see them all there. There's also a very healthy lineup of events on the Pipeline Industries Guild website. If you just Google events Pipeline Industries Guild, a couple that are coming up very soon. We've got in London a showcase and the Lion's Lair Women in Engineering on February the 10th, and then on March the 8th, Professional Development Network Annual Training Day, how to understand and deliver optimal performance. There's an innovation and achievement seminar in March on the 8th, and first big dinner back of the year in 2022, March the 8th. We've got the 64th Guild dinner in London with some keynote speakers at that event. Okay, Bob, I'll hand over to you on this one now and let you crack on.
Lovely. Thank you, Ivan. Good afternoon, everybody. Thank you so much for joining this webinar today. I'm absolutely delighted to be able to present to you. This is not my first presentation, but my first one with the Guild. So I'm looking forward to getting stuck in. I've got loads of content today. We're going to go on a kind of source to tap-ish high-level overview of the major treatment works that supplies Bristol, and it's called Perton. Before we get going, just a really quick intro about myself. 18 years in the water quality team. Bit of a boy to man story, actually working at Bristol Water. Went to University of West of England, studied geography, did a little bit of travelling after that, came back, wasn't quite sure what I wanted to do, but ended up getting a job with Bristol Water as a water sampler. And from there, literally just climbed the ladder as a trainee scientist, fully fledged water quality scientist. And now I'm a water scientist and I also manage some of the sampling technicians as well. Fascinating job. I still absolutely love it, and I hope that comes across in the presentation today. The job takes me everywhere from raw water, so the lakes, streams, aquifers, through each stage of every treatment process that we operate. We have about 15 altogether. It takes me out into the network, to service reservoirs, the big trunk mains. I look at the distribution system, and also get to speak to customers on a daily basis, sometimes go into their properties to see if we can work out why there might be some quality issues there. So I get this really good overview of all the operational aspects of the business. Here's just a few pictures of me over the years doing various duties. So I love it. Some of the work's in the office, sometimes it's doing a bit of lab work, sometimes you're underground in structures, sometimes it's playing with the treatment works and doing optimization work. It is fascinating. Okay, so on the agenda today, we're going to do just a really quick overview of Bristol Water. I'm going to introduce you to Purton. We're going to talk a little bit about source quality, and then I'm going to take you through the treatment process at Purton. It's very difficult to do these things justice, I think, by a slideshow. You can't beat just getting out there in the treatment works and just seeing it, smelling it, touching it. It's a very sensory experience being in this giant machine that's producing water. So what I've done, I've made this presentation very lots of pictures, not too much text, so we can whiz through the treatment process relatively quickly. Where we do encounter some of the technical phrases, I'll explain those as well. There's lots of technical words in water treatment, but hopefully we can demystify some of those as we go along. There'll be time for questions at the end as well. So just very quickly, where is Bristol Water? We're a very small water company. We are a water-only company, so we don't do any of the sewage activities. It's purely based on drinking water. And where is Purton Treatment Works? We're right up in the top right by somewhere called near Sharpness, and this is the major treatment works for Bristol. So we pump water from the treatment works down to somewhere called Pucklechurch, which is our big surface reservoir, and then we feed the city from the east, and it also feeds the northern parts of the city as well. Maximum output 165 million litres per day. So that's over a third of the entire water that Bristol Water actually produce. It is the big one. It was built in the 60s, and as Bristol's grown, so the treatment works has grown as well. So before we start talking about how we treat the water, we need to understand what's in the water first, and by understanding the source quality, this helps to show us why we have the various treatment processes in place that we do. Now, Bristol Water have the two major treatment works. You've got Purton in the north, which takes water from a canal, and we have Barrow in the south, which takes water from reservoirs. Surface waters that are in reservoirs, generally more easier to treat, certainly for us. The quality will shift seasonally, so it's easier to anticipate changes in quality. For instance, late spring, early summer, we know that we're going to get algal blooms on the reservoirs, and we can adjust the treatment processes up to be in readiness for that. So you can be more prepared with lakes because of the gradual shift in quality. When it comes to Purton, we abstract water from a canal, and because the source is generally more flashy, more volatile, so we're more prone to weather conditions rather than seasonal conditions. When it rains, water lands on the surrounding fields where there's herbicides, pesticides, animal muck. All of that gets washed into the canal, and very quickly the quality can shift. Increase in pesticides, increase in sediment, the colour of the water, bacteriological quality. And so Purton is a more intensive treatment process, both chemically and in terms of energy as well. But the canal source is also more risky because it can change very quickly. We have to be able to respond very quickly to those changes. So here's an example of something called turbidity. This is a general indicator that we use for the amount of stuff, particulate stuff, usually in water. It's a measure of cloudiness, and the unit of measurement is NTU. So as you can see, particularly in 2020, we had some quite significant shifts in quality, mainly the amount of sediment that was in the water. Also, the amount of colour of water can shift very quickly as well. We do still tend to get the seasonal fluctuations, but it can just change within 48 hours. So you can see the spike, particularly in 2020, when we reached an all-time high of over 45. That can occur within a few days. Nitrates as well. Nitrates are very stubborn to remove during a treatment process. So we actually have to blend water. We don't have the treatment process in place to remove it from the water. So we take some low nitrate water, some water with the high nitrate, and we mix them together to bring us below the 50, which is the drinking water standard for nitrate. I'll come on to the standards a bit more as we go along. E. coli. Most people have heard of E. coli. It's one of our indicator organisms we use as a measure of bacteriological quality. We seem to be getting worse as well from 2019. This is all in the raw water that's about to be treated. It's to be expected if you're taking water from a canal, and surrounding the canal is lots of agricultural land. And I'll explain how we disinfect the water in part 2 of this presentation. Algae. We don't get as much algae on the canal as we would do in a reservoir. Because the canal is faster flowing, we don't get the algae settling out, or you don't get them growing as much, but we still get some blooms, low levels compared to a reservoir, but sometimes at peak levels it can be enough to affect our filters and affect how we separate the solids from the water. And then we've got something called Jasmine, which is it gives you a kind of hay stack, rotting leaves, those kind of smells you get in the water. We do tend to get peaks of Jasmine. We can take these out quite easily, but the water does get quite smelly at certain times of year. Again, it's just something that we have to be prepared for. And then pesticides. I've used glyphosate just as an example, good old weed killer. This is used in abundance on agricultural land, and again you can see we do get some quite significant spikes in glyphosate. We also have a measure of total pesticides, which is a parameter that just measures a whole suite of different pesticides, and they kind of lump them all together. Again, pesticides are a challenge. It's something that we understand because we do lots of work with the farmers. We understand the catchment and we understand what pesticides are being used. That said, pesticides can be very stubborn to remove, particularly something like Metaldehyde. For those who haven't heard of Metaldehyde, if you know those little green pellets that you can put on your marigolds to stop the slugs eating them, those little green pellets, the active compound is Metaldehyde. Farmers around the catchment of the canal will spread these little green pellets everywhere. Really good at killing slugs, and that's what they're there for. You can, very, very effective, actually quite cheap as well. However, Metaldehyde is really difficult to remove during water treatment. And as such, we have seen some treated water, which is the green trend you can see, treated water spikes in Metaldehyde, which corresponds to the blue, where it has spiked in the raw water. So difficult to remove. We have actually looked at, rather than investing in treatment processes to remove stubborn Metaldehyde, we have a really good program of work with the farmers around the catchment, and we've been using an alternative slug pellet, one which is ferric based. It can be quite difficult as well to get the buy-in from farmers. This is their livelihood that's on the line. But there has been adoption, and it has been effective at killing slugs. And as a consequence, we've been able to see a gradual reduction in treated water Metaldehyde, and also in the raw water as well. So I think that graph tells a really nice story from as of 2015. 2013, we started to see the adoption of this ferric, and it seems to be working. So not all the solutions are engineering out of treatment works or throwing chemicals at it. Actually working with farmers to try something different can actually have a greater impact, both on Bristol Water, but also the ecology of the catchment as well. So it's a good news story there. Finally, zebra mussels. So these little critters came across in the 1800s, stuck on the bottom of boats. They then infested England, gradually infested British waterways. And this is all about the biomass. These things will just stick on the inside of pipes, structures. This photo on the right was it's taken from Northern Ireland water. But if you don't deal with your mussel problem, they will grow and accumulate to a point where they will restrict pipework. This is a raw water main, so this is water coming from the source going into the treatment works. If left unchecked, they could completely block your pipes, which means that you won't be able to get water into your treatment works. We've been exploring different ways of killing zebra mussels. Historically, it's always been chlorine, but we are looking at alternatives. Okay, that's part one. So part two, we're going to get into the meat of it now. We're going to take you through each stage of the treatment process, explain why we use those chemicals, and we'll explain a little bit about distribution as well. So where does it go once it's been treated? So here we have a list of the various treatment processes. I'm going to go through each one of these over the next few slides. Purton, as you can see, is quite a substantial treatment works, about 10 different stages altogether. Here we can see the canal. Purton's in the purple box and the intake is in the yellow box. So we abstract water, we pump it from our intake into some storage tanks. Now this gives us about half a day's worth of storage. It's useful to have some pre-stored water there. For example, if we had some nitrate coming down the canal, we would run just from the raw water tanks, let the slug of high nitrate water pass by the intake. When we're confident that that's passed by, we can start taking water direct from the canal again. So it gives us a little bit of resilience. Here's another picture of the intake. We actually use something called band screens, which are these giant revolving screens. These are good for taking out all the large stuff that ends up in a canal. Sticks, fish, welly boots, shopping trolleys, potentially. You get some quite interesting things that get lifted and kind of flicked over into this big pile. Once we filter out all the really big stuff, then we pump the water into the treatment works. I mean, some of these pumps are absolutely massive. There's so much energy being used here just to get the water into the treatment works. Then we have our blending. So sometimes we can take direct from the canal, sometimes we can take from the raw water tanks, depending on what's happening with quality. Now the first chemical stage of treatment is the addition of sulfuric acid. Now the water that Bristol Water treat is alkaline, generally around pH 8. For the next stage of treatment, we're going to be adding something called a coagulant. It's a bit like a glue. So it's a liquid that we add to water and it sticks all the bits together and those bits are going to settle out. In order for that liquid coagulant to work, we need to dose it into the water when the receiving water is at a pH level of around 7. So our raw water is pH 8. We add a small amount of sulfuric acid just to reduce the pH to pH 7. That's in the right target range, so then we can then add our coagulant. Here we can see the acid control. So as the top trend is showing the pH of the water, and the bottom trend is showing the stability of our pH. Anybody out there who's done any work with acids and pH meters will know how tricky it can be to actually fine-tune pH. We've got water coming into this treatment works, potentially 165 million litres per day, and we're using an acid strength which is 96%, really strong. So it doesn't take a lot of acid to have a big drop in pH. So the control systems and the algorithms we use for pH correction need to be absolutely spot on. And this is where I find it absolutely fascinating. You can take millions of litres of this, tons of this stuff, and then what you get is really fine control. These systems have been continuously tweaked and adjusted by our ICA technicians over many, many years, and it is a fine art, but it's working really, really well. Once we're happy that our pH is in the 7 range, we can then add our coagulant. Alkalinity can also have an effect as well. So the water that Bristol Water treat is classed as hard, and that means that there is lots of calcium and magnesium minerals in the water. When we add acid to water which contains those minerals, it's almost like it sponges up our acid. There's a demand there. So water with high alkalinity can have a greater buffering effect. So it means we need to put more acid in to counter that. And here we can see the seasonal fluctuations in alkalinity. So the price of water, not for the customer, but certainly for us, can fluctuate on a seasonal basis as the alkalinity goes up and down. Because when it's high, add more acid. When it's low, add less acid. So it's important to remember that the quality is always changing, and that's one of the big variables. It's not just about the millions of litres of water and tons of chemicals. It's also this continuously fluctuating quality that we need. So it's constant optimization and adjustment needed. Coagulation. This is a very standard approach to treating water. We use something which is a bit of a mouthful. It's called polyaluminium chloride, or PaCl. In essence, it's a glue. It's a liquid aluminium glue. It's very positively charged. We add it as a liquid into the water, and we're adding it in this orange area here. I've got some other photos in a sec. If the pH is right, if it's 7, and you add this aluminium liquid to the water, when it hits the water, the liquid will change almost instantaneously into a particle, a very fluffy particle that's positively charged. And these particles will start to attract all the stuff that's in the water, all the particulate matter. Because they're very sticky, they'll all start to bind together. So you start to form bigger and bigger lumps. Here's the coagulation tanks here. So the water is being pumped into the treatment works, into our coagulation tanks. And here we can see the water being, the chemical almost being drizzled into the water. We have a series of mixers. So we want a nice homogeneous mix of all our coagulant and our glue, sticking everything together. Where possible, we try and use little waterfalls. It's free, so it encourages good mixing. This here's the flocky material. You can see it looking very. It is very fluffy. It can sometimes make the water look a little bit blue as well, but it's that flocculated material that's all stuck together that will eventually start to settle. Now we use something called hopper bottom clarifiers. Huge structures. The water with all the coagulant in is put into these big hopper bottom structures. The coagulant is heavy, so all the bits will end up settling down to the bottom of the clarifiers. And it's the clear water, this picture on the left shows it quite nicely. There's clear water on top, which we then take off, and then we send that through to the next stage of treatment, which is filtering. All the solid ends up getting drained out of the tank. We pump it out, and there's a separate waste treatment process for managing the sludge that's removed from settlement. I'm not going to include the waste aspect in this presentation, but just to let you know that whatever we add to the water, that also has to be removed in order to treat the water, and that waste has to go somewhere. We have different types of settlement processes. These ones are pretty cool. They're called super pulsators. These are flat bottom clarifiers, and they have something called lamella plates on the inside. So whereas hopper bottom clarifiers, a big tank like this, these are flat bottom tanks. And the picture on the left, you can see the slightly thinner bit to it. That's like a vacuum. So it will draw up some of the water and it will push it down, and this pulse will send ripples through the clarifier, and that's supposed to encourage all the particles to kind of stick together and stick onto the lamella plates. The super pulsators were added as Perton expanded, and we needed some, it's like a bolt-on process to keep up with demand. The next stage is filtration. We have something called rapid gravity filters, often referred to as sand filters. So once the water's been coagulated, we're going to send it through to our filters. And here they are. They've got 7 filters altogether, and they're packed with a black sand called anthracite. The basic giant sand pits that are about 1.5 meters deep. These filters are really good at taking out the remaining solids that got carried over from our clarification process. Clarifiers will typically take out about 90% of all the solids. Our rapid gravity filters, and the clue's in the name there, will take out the remaining bits from the water. Now, these filters can also be backwashed automatically. So depending on what we call head loss, depending on how much they're blocking up by doing all that filtering, it will send a trigger which will start some backwash pumps. The water will then, instead of trickling down through the filter, we push water back up the other way, and that helps to remove any solids that are stuck in the filter media. Really reliable, and again, it's a fairly conventional way of treating water: clarification plus filtration. The next chemical stage is something called ozonation. Ozone is a very good, it's a very strong oxidant, and it's really good at breaking down things like colour, taste, smell, pesticides, also metals that are dissolved in water, things that can't necessarily be taken out by our filters. Dissolved metals can be oxidized using ozone. Really, really versatile treatment chemical. We take liquid oxygen, we put it through a generator, which is on the left here, and that converts the liquid oxygen into ozone gas, O3. Ozone is then released by diffusion inside the tank, and it's all those microbubbles that do all the oxidation and can break down all those parameters I've just described. Really, really effective. And it doesn't leave a residual in water as well. It can, however, cause some treatment problems if it's not well controlled. Bromate is a challenge for us. If you have bromide in your water, which we do, and you add ozone to water, there is a risk that you form something called bromate. And the drinking water standard for bromate is 10. So there are times when we have reached 10 previously, back in 2017. Usually we sit around, on average, around 4. But it's something that we have to monitor the raw water very closely to look at the amount of bromide. Then we have to adjust our ozone dose to make sure that we're not going to exceed the drinking water standard. The next stage of treatment, once we've added our ozone, is we stick it through some more filters. This time we use GAC filters, granular activated carbon. So these are different to the other filters we just described. GAC, or activated carbon, is really good at absorbing dissolved things from water, things like smell. You can find carbon filters in like Brita filter jugs. It's the black granulated stuff that's in the cartridge. These filters are amazing at absorbing colour, taste, smell, pesticide. So in combination with ozone, these two things are great at solving our pesticide problem. Once the water has been through the activated carbon filters, really by this point, we've removed all the particulates from the water that we're going to. We've oxidized as much as our dissolved stuff that's in the water, whether it's metals or pesticides, color, taste, smell. All that's left to do now is to disinfect the water. So we're going to remove bacteria, we're going to kill bacteria, viruses, to ensure that the water is safe to drink. Now, it's only been, we're going to use UV irradiation or UV light to do the disinfection. UV has been around for a long time, but for a lot of water companies, it's only been more recently that it's been adopted. For Bristol Water, it's been since 2017. We've really been using UV in anger. We now have UV at all of our major treatment sites, and quite frankly, it's absolutely brilliant. We have the reactors themselves are very small, so water comes through. You can see the green pipes. The reactors are these small stainless steel units here, and then the pipe continues at the other end. Inside are around 30 strip lamps, and that's the flow of water. Whereas for suntanning, you have UVA and UVB that you get from the sun. You also get UVC, which is the biocidal range of the UV spectrum. So we're using UV light. It's the same light you get when when you're doing welding, you have to put the mask down. It's because of the UVC radiation that can be extremely harmful. Now, I think the potency is such that even if the water only comes into contact with UV light for literally about a second, which is in this case at Purton, that is sufficient to kill off the bacteria and the viruses that's in the water. The UV is that intense. Now, in order to get the UV light into the water, we need to make sure that the water itself is clear. We use something called transmissivity. You can see it on the left, 98.4 as an example. So Coca-Cola, for instance, if you shine a torch through a bottle of Coca-Cola, you're not going to get any light coming out the other end. That would be a transmissivity of 0. Ultra pure water would have transmissivity of 100%. So that's the spectrum. So we're on 98 here. So the cleaner or clearer your water is, the more UV light can penetrate the water. If your water's got lots of bits in it, if it's quite turbid, then the UV light can be intercepted by those bits in the water, and your disinfection isn't going to be as good. We use UV light, yes, for bacteria and viruses, but for also other organisms. In particular, something called cryptosporidium. Most things are killed by chlorine. However, cryptosporidium is something that, because of the way it lives in this kind of little egg, this protective shell, chlorine isn't able to penetrate through its shell. Cryptosporidium you can typically get from animal intestines, and it can make you really, really poorly. Yes, we can filter some of these things out, but ultimately some of them do get through. And if something is resistant to chlorine, you need something else in place to be able to deal with it. And this is where UV light comes into its own. UV light can actually penetrate through the protective shell of the organism, and it doesn't kind of explode them, but it corrupts their DNA so that they can't reproduce. So they're still there, they're just inactivated and rendered harmless. Chlorine. We're getting to the final stage now of water treatment. Chlorine is a tried and tested chemical that stood the test of time for water treatment, in part because it gives us a residual, so it lasts a long time, which is good. That gives us some long-lasting protection of water. We used to put in a high dose of chlorine to kill overkill, in essence, to kill off lots of the bacteria and viruses. But if you put in too much chlorine, people won't be able to drink it because it would taste horrible. So we'd actually dechlorinate the water slightly before we send it out into distribution. Now we have UV light. UV is the primary disinfection. It's killing off all of the stuff. And chlorine, we add a smaller amount in to just provide a protective residual as the water is travelling through the network. If we didn't add chlorine, the pipes connecting the treatment works to Bristol, over time they get very slimy. Things will start to grow, and with things growing inside the pipes, you're more likely to start getting musty tastes and smells, and all the bits that grow could potentially slough off and be carried through the network. So it's there to provide protection to the water as it makes the journey into Bristol. So, lovely, thank you, Van. We actually produce our own chlorine on site, something called on-site electrochlorination, or OSEC. We used to buy it in gas. When you're dealing with gas chlorine, it's extremely dangerous. Now that we're able to produce our own, you see, with giant tanks full of salt and some electrolyzers, which is that salt, and form sodium hypochlorite, switching from gas to liquid, it's saved on its health and safety. It's much more improved, but also the logistics of, we don't have to bring tanks and tanks of chlorine gas to the treatment works. We can just produce our own on site, and we'll see this more. This will be rolled out more to other sites as well, smaller remote sites where we can just have a small setup, a small electrolyzer with a brine solution and a receiving tank, and you can just make your own. So this will become more commonplace. Here we can see the trend at the bottom. You can see the chlorine residual. Typically leaving Purton treatment works, we have a chlorine residual of 1 milligram per litre. As chlorine will dissipate from the water over time, so it will gradually reduce. So we put a level of 1 at the treatment works. By the time it's getting to Bristol, we could be down at around 0.5 milligram per litre. The further you live from the treatment works, the less chlorine you will have in your water because it will reduce over time. During the summer, the chlorine will reduce more quickly when water temperature is warmer, and in winter the chlorine is held in the water for longer. So it's not that we put any more in, it's on a fixed dose, but depending on temperature you could receive a bit more at certain times of year. Now these processes have to be extremely tightly controlled, and we've got lots of safeguards in place. So when it comes to disinfection, we often have dual validation of certain things. So for instance, when we dose UV light, we're measuring it in different ways. You don't just have one sensor to tell you whether or not you're disinfecting something, you have multiple sensors. Arguably, disinfection is the most important stage of water treatment. We are, the population receiving water from Purton is over 400,000 people. If Bristol Water don't get it right, then we can affect the health of a lot of people in a very short space of time. Typically it's around 24 hours by the time the water has been treated, by the time it's getting to somebody's tap in the supply area. When you've got so many people all drinking that water from the same site, it's imperative that you have the right safeguards in place. When it comes to disinfection, if the amount of UV light was to reduce, the process will shut down. If we can't guarantee that we're disinfecting the water, there's very quick shutdown procedures in place to make sure that that water isn't going out into distribution. With chlorine, we have a 0.3 plus or minus 0.3 margin either side of the target dose. So if the chlorine was to go to 0.7, then it would shut down. If it was to go to 1.3, then it would shut down. And we have chlorine being measured from different analyzers as well, so you're not just relying on one analyzer. Once we've disinfected the water and we're happy with quality, we then pump the water out into the distribution system. That picture in the middle is a picture of me, just to give you an idea. I'm 6 foot, so they are pretty hefty pumps, and we've got 5 of these high lift pumps, all pumping the water down into Bristol. There's a few different pumping stages that we've seen. One is the raw water, to get the water into the treatment works. We also have an intermediate pump set that pumps the water from the filters to the ozone stage. And then at the end of the treatment works, we have these big high lift pumps to boot it down into Bristol. The photo on the left, you can see some of the analytical equipment that we use as well. We're measuring pH levels, we measure chlorine, we're measuring turbidity. We're also measuring conductivity as well. Electrical conductivity is a really good indicator of whether something isn't right. The more stuff that's in water, the higher the electrical conductivity will be. So we don't necessarily know what would be wrong with the water, we just know that something isn't right. So, and with all these different instruments, you can set high warning alarms, but also high level alarms as well, which will shut the treatment process down completely, just stop the pumps. Once we've treated the water, we're going to pump it down into something called a service reservoir. Bristol Water have over 150 treated water structures throughout its company area, positioned at some of the strategic high points. So we, at certain times of day, will pump the water, usually when everyone's asleep. We will pump the water to fill up all of our concrete storage boxes, ready for when people wake up in the morning. So then we have our first demand period when people want their showers and are waking up, having their breakfast. The level of water in the service reservoirs will go down. Then everybody goes to work, and that's our time to start filling up all our structures again, ready for when people get back from work. So we have this twice daily demand period. Pucklechurch is it's just on the ring road, just to the east of the city, and it's the equivalent to about 2 football fields internally. It's in 2 compartments as well, so if we need to take one out of service for maintenance or inspection, we've also got the other one, but normally we run both compartments at the same time. They are absolutely massive, but you wouldn't even know they're there. Most of them are kind of built underground with a little grassy top, so a lot of the assets, although they're at high points, they are kind of well disguised, to the point where often staff can find it difficult to find some of the structures sometimes. Purton is arguably the most important strategic asset that we have. As a consequence of that, the security of the site is absolutely fantastic as well. And it's continuously monitored by cameras, listening devices, high security lids. Here we can see the demand period, or the intervals, if you like, from when the structure fills up to when it reduces. Now, Purton Treatment Works, because of its strategic importance and because there's so many people that it supplies, it can't really shut down. We can shut it down for 8 hours, potentially, for some maintenance, 12 hours, maybe. When we're getting to, well, more than 12 hours, people are getting very fidgety. So not only does the quality have to be exact, because of all the people downstream that are receiving this water, also sufficiency of supply. We need to make sure that people get water as well, continuously. The economic impact of failing to produce water, it can be huge in a very short space of time. So there's a big responsibility, and I suppose that's the trade-off. You can have one big treatment works, you've got lots of eggs in one basket, and you can really refine that treatment process to make sure that it can treat the water consistently. However, if you do get problems, you don't necessarily have the resilience as what you would do if you had lots of little treatment works all supplying the area. Purton can also supply water. We've connected our network up to allow water to travel down to the south, south of Bristol. Again, we can receive that kind of puts the burden, shifts the burden further, where we need to, if Barrow treatment works, for whatever reason, was out of service, we can have Purton water coming all the way down into the south. So the population supplied is potentially even greater. Now, there's an awful lot of information there, and we are just coming to the end. I think that's it. Ivan, how are we doing for time?
That's perfect. Perfect, Rob.
Excellent.
Got 10 minutes for questions. If anybody, I think I'm getting a slight bit of echo, so anyone can put your mics on mute to just open them up if you want to ask Rob a question. Matt's going to come on. There's a few questions that have come up on the chat box if no one's asked anything, and I think we'll just kick off with those. Over to you, Matt, but please ask a question, put your hand up if you've got something for Rob.
Okay, thanks, Ivan. First one's from Pierre. Is there any value in the sludge produced? For example, is it suitable for reuse in agriculture?
Good question, Pierre. Thank you. Now, some of the sludge for Purton treatment works, we don't send it to. It doesn't have any agricultural purpose. It actually gets discharged to the estuary with a certain high tide windows. However, at Barrow treatment works, the sludge that we produce is more favourable as a bulking agent or a soil conditioner, and so we do have agreements with farmers in the area where we actually pay them to take the sludge. They put it in their silos, and then they can integrate it into their fields. It's very rich in phosphates. There are some new regulations coming in about the phosphate quantity of sludge, and so we're a bit unsure at the moment what the future is looking like. At the moment, we've got this win-win situation with the farmers. In the future, it may become more challenging because of phosphate. But no, really good question.
Okay, next one's from Rod. Sorry, pronunciation. Chloroamination not been adopted by Bristol Water.
Chloroamination, no, it hasn't. We used to in the past, but not for very long. It's always across the board. We just use free chlorine residual for our disinfection, and it's not something that we're looking to change either.
Okay, next one from Natalie. Crypto testing is quite expensive. Do you monitor the raw water for it too?
Yeah, good question. Thank you. Yeah, cryptosporidium, we do a series of grab samples on a weekly basis. So we fill up it's 10-litre jerry cans and we send those off to the lab. On some of the sites, we also have crypto rigs where we continuously pump water through a filter, and then we take the cartridge out and we send those to the lab to be analysed as well. So we are sampling both the raw water and the treated water for cryptosporidium.
Okay, next one from Ivan. What is the carbon filter's main purpose and how does it work?
Carbon filters, so they work by absorption. So think of them as kind of sponges. So they're not there to take out the particulate matter. They're not there to take out bits. They are there to take out the things that cannot be filtered by normal sand. So they're inside, if you look under the microscope, they're very kind of fissured and almost a bit like honeycomb. So the actual surface area of the carbon, because they're so porous and honeycombed, is absolutely enormous. It's a wonderful stuff, and you can have activated carbon of lots of different materials, from bone or from coconut husk. You know, there's lots of wonderful materials that can be used. We actually have a carbon regeneration plant on site where we can drain out the filters, goes to a pipe underground, pops up in a place called Perton Carbons, or Norwich Carbons as it is now, and they regenerate our carbon for us. So after 10 years of sponging out pesticides and taste and smells from the water, the carbon gets exhausted, so it needs to be regenerated, acidified, and they stick it in a furnace and heat it to about 900 degrees before it's then further conditioned and then put back into the filter, ready for use again. It's wonderful stuff.
Another one from Ivan. What are the future treatment challenges for water companies, do you think?
Future treatment challenges. I think the challenges for us would be ever tightening drinking water standards. So we have World Health Organization standards, European standards, and then we have the standards for England and Wales. And arguably we have some of the most stringent water quality standards in the world. The parameters, as more research and there's greater understanding as that's done, the standards will never get relaxed. They're only ever going to get tighter. Lead is an example of that. The standard used to be 50 micrograms per litre. 2013, that was changed to 25 micrograms per litre. The standard for lead in drinking water now is 10. And no doubt in the future, it's going to be, I don't know, less than 10. So it's going to be tightened all the time. I think lead is going to be the biggest challenge. It's not so much that this comes from the source water, though. It's not a treatment issue. It's more about the pipes that are connecting properties to the mains. So Bristol has almost 50% of the lead pipes in the city centre area. Are just really old and need to be replaced. But it's a huge scheme of work to remove lead from the water. Good question, Ivan.
One from me. This is, does increased catchment management offer the potential to reduce the process cost?
Yes, it does. Yeah, absolutely. I don't have those numbers, but we have a small team, particularly in the Perton catchment, that have been working with the farmers, and particularly around the Metaldehyde project. I suppose for us, in the short term, it actually increased our operational cost because to get the farmers on board, we were paying for the alternative slug pellets. So there was an ongoing cost for us, rather than asking the farmers to put their hand in the pocket initially. This new wonderful material that they could try, we paid for it all. However, since then, it's been adopted and we're not having to pay for it. So arguably, yes, in the long term, there will be cost savings.
Okay, final one from the board from Roddy. Has the high energy use required by the treatment works pump supplies been reviewed to see if renewable sources are available?
Yeah, good question. Thank you. We're currently looking. We have PV cells already in place. So the final treated water tank at Perton, where we add the chlorine to the water, it's a huge surface area. So we filled that with PV cells. That was a success. It's been there for at least 8 years now. That's probably been our biggest enterprise when it comes to green energy. But we are always looking at optimization of the pumps where possible. And at some point, the pumps will have to be replaced completely. Because they are getting old now, and so you can improve the efficiency by getting better pumps put in.
We've lost Matt there. There's one last question there, which is how long does the coating of lead pipes by orthophosphoric acid last? Does it wear off? And is that why we keep having to dose?
Yeah, good question. So to combat lead pipes dissolving into the water, we add something called orthophosphoric acid at the final stage of treatment. Orthophosphoric acid will form a scale a protective layer on the inside of lead pipes, which allows the water to pass through the lead pipe without coming into contact with the lead. Again, I don't have any science, any data to hand. 5 days is what we typically would say. We would be uncomfortable with having our dosing equipment off for 5 days. Because we're in a hard water area, we're in a more favourable position in that hard water in itself has a scaling effect. Whereas if you're in a softer supply area, then that protective layer would erode much quicker. But 5 days.
Thank you very much, Rob. That's brilliant. Have we got any last questions for Rob before we wrap up? If you do have some that come up after this, do fire them in. We'll try and answer them. While we're waiting for any last questions, just want to say thank you, Rob. You kind of explained it. It really was a whistle-stop tour, and you avoided the jargon, but it really in depth at the same time, and just showed quite clearly all the different processes involved in, making wholesome, safe water. So a big thank you for doing that. Those of you who joined in halfway through, this is going to be recorded. It is recorded. It'll be on the Pipeline Industries Guild YouTube channel. There's a lot more webinars and events coming up. Have a look on the Pipeline Industries events website. And I'd like to say a big thank you to Rob, Matt for doing the questions. Thank you for Kate and Kath at HQ for hosting this for us. And thank you everyone who's tuned in.
Thank you, everybody.